Okay. Okay, guys. Good morning. Welcome back from just a short break on Tuesday. You guys enjoyed? Yeah, it's good. We had exam before the break, right? I know you guys still have deadline for the project, and then of course our final exam, even though it's only one chapter, but I think it's 40% of the final grade. So it's a big exam. And as we promised, the last and the final exam is going to be on this chapter 7 only. So you guys can be assured that if you're really good at mastering this chapter, you're going to be doing well in the final exam. So that's the purpose. But of course, you can see from the next couple of slides, you're going to see a lot of the contents are referring back to the equation that we learned before. Yeah, go ahead.
Is the final, so you said the final was going to be 6 questions and still drop the lowest as well?
No, actually the final is 5 problems as well.
5 problems drop lowest?
Yeah, we're going to drop the lowest.
So
yeah, hopefully.
time.
No, it's the same 2 hours. Yeah. Oh, no, actually it's 2 hours. It's 2 hours. So it's a bit more, it's more depth, I would say. Same number of problems, but a little bit more depth. And I cannot guarantee that each question is independent, but it may be some, you might have to refer to the previous answer for the next question. Yeah, it's just impossible to isolate, all 40-hour questions. So yeah, but it's all that you learn in the class. If you guys pay attention to the lectures, review the lecture, review the material, do your homework, I have no reason that you don't get 90%.
The homework is substantially larger
than homework is much more. I mean, the way to do this class is to do a lot of practicing.
Yeah, of course.
You don't do practice, you look at the question, yeah, I know it. But then, turn around and you say, oh.
I'm just asking these questions
Yeah.
so I can better manage my time.
Yeah. Okay. So any other questions? No? Okay. So what are we doing in this chapter? So we are taking our BJTs and MOSFETs and use them to build amplifiers. And so by name, in chapter 1, I believe we mentioned a little bit about amplifiers. What amplifiers do, they take an input, they make it bigger. And not always. Like towards the end of this chapter, you will see we have emitter followers. We don't make them bigger. We follow the input, which means the output is going to have the same amplitude as the input. And then what's the purpose? Well, we change the input resistance and we change the output resistance. And we also had a little bit talk about why input and output resistance are important. Because if your input resistance is too high, if your input resistance is too low, that makes a big difference. If your output resistance is too large and your load cannot take all the output, right? If your input resistance is too small, then your actual input in comparison to the source is going to be too small. So you're not going to amplify, right? So we have all those things together. So what we're focusing on is basically just focused on the small signal operation, which means we amplify small signals. When we say small, we do mean small. When we particularly in this book, we're not talking about really small, but we're talking small. What does it mean? For example, if you look at say AAA battery, it's 1.5 volts, right? So that's kind of typical voltage. If you look at the 9 volts battery that you use for your smoke detector, that's 9 volts. So that's like general numbers that we deal with. And a small signal is typically 1,000 times smaller than that. So you look at the millivolts, milliamps, okay? That's what we mean small. But in fact, what happens is that the technology has really progressed. So the milliamps that we're learning today, the principle is the same, but the actual transistors are going to microamps. It's another 1,000 times smaller. They might actually go to nanoamps to work, just because you have, on a typical on a typical CPU, like iPad, you got a couple billion transistors on it. So if transistor consumes 1 milliamps, you're looking at thousands of amps. So it's not possible, right? So you have to really cut it down. But again, the principle is the same. You can still use the same theory. It's just like the quantities are different. So we're going to really look at small signal. And after we derive the small signal models for BJTs and MOSFETs, we're going to go over to the basic configurations. The basic configurations are going to have, I think we touched this a little bit earlier. We have 3 types of amplifiers. We have, say, for BJT, we have a common emitter, common collector, and common base. And for MOSFET, we have common source, common drain, and then common gate. So there are like total 6 types of amplifiers. So we're going to look at each of them. And all of these configurations are going to be based on the equivalent circuit. So by the time you move away from BJTs and MOSFETs like we learned in chapter 5 and 6, and in this chapter quickly, we're going to move on to the small signal model. We really use them because whenever you saw this transistor, just translate it into a small signal model. And the next step, what you do is to use circuit analysis. So what you're doing is really, so that's why this class towards the end, you think, oh, it's so simple. Because what you need to master, the small signal model, number 1. Number 2, you need to know how to solve circuits. Not so much about electronics, actually, it's circuits. You know these 2 things, you can solve all problems. Every single problem, you should have no issue to do that, okay? Of course, we're going to talk a little bit about biasing, because biasing is important because we have to make the circuit in a certain mode. Like in MOSFET, it has to be in a saturation mode. For BJT, it has to be in active mode or linear mode. So those ones, how do we make sure that they are? If they like move out of those regions, your amplifier going to the like a nonlinear region, it's no longer amplifying what you need. It's still going to amplify, but it's going to like give you an incomplete output waveform. Like it's no longer going to be a sinusoidal waveform if you want it. You might have a cutoff at the peak at the bottom, right? Either or both, or peak or bottom or both, right? So we have to make sure we do the good biasing. And of course, the basic discrete amplifiers is the 6 types that I talk about. We're going to go through each of them. So we're going to have total 6 lectures on this chapter, including today. So that actually, because we have a break during Christmas, we had a break on Tuesday, right? So we lose 2 lectures. And on December, I believe December something, the second week of December, we're going to have the invited speaker from SMO. So that's a good one. You guys should really be here. And then the last lecture, I think I'm not going to do new contents, probably just going to do some review or Q&As with you guys. Okay. So we're going to move on. Okay, those are the 2 basic configurations of MOSFET and BJT to make sure they operate in this region so that we can use them as amplifiers. So for MOSFETs, you guys remember, what do we need to do? We need VGS to be larger than VT, to be not in cutoff, right? And then VDS, the 2 conditions. Another one is VDS has to be larger than VOV, yeah. And VOV, of course, is over drive voltage is VGS minus VT. So how much VGS is over VT? So first of all, VGS has to be larger than VT. And then how much is over? That's called overdrive, right? So VDS has to be larger than VOV, to be in saturation mode. And once it's in saturation mode, we have the current expression. It's got ID. It's 1/2 Kn. This Kn is like Kn prime times W over L. Sometimes we use this Kn in place of Kn prime times W over L. And then the inside is a VOV squared. So very simple expression. Now, and then for BJT, what are the conditions for BJT to be in active mode? Remember, it's not saturation mode anymore. So we switch gear. It's going to be in active mode or linear region. For BJT, for BJT to be in the linear region, we have to make sure that VB is near 0.7 volts or approximately 0.7. It could be a little bit more, could be a little bit less, depending on how much current we need in the collector. And the second condition is VCE. VCE now has to be larger than 0.3 volts. So it's not in saturation. If it's below 0.3, it's going to be in saturation. Or it's fully in saturation, or sometimes called deep saturation, it's going to be 0.2 volts. So from now on, we're going to have to maintain these two conditions. So at times, you are required to verify whether it is in the right mode of operation, okay? So just, most of the time, if they don't ask you, basically it's assumed, okay? But if it asks you, then you have to verify. So it's just a little bit, pay attention to that. Okay, now from now on, we're going to distinguish some symbols, okay? Now it's, in print, it's easy, but while I write it, it's going to be sometimes confusing, okay? But I just don't have a good handwriting. Unfortunately, I was not trained very well. So there are a couple of things that you guys to distinguish. So for MOSFETs, we're going to use like ID for total. It's total current. So for IC, we use like capital C. And then we're going to use ID for DC or biasing. And here, of course, we use IC. And we use
DC.
Yeah, for DC current. And for ID for small signal. So here will be like I little c. So that C is difficult because C capital and the lowercase really just big or small, it's the same. Of course, when you get to voltage, it's going to be the same. You're going to have V, like VGS, you probably can think about what this is. This is for the small signal, the lowercase V and lowercase GS. So what just remember is that both lowercase is for small signal. Lowercase plus bigger capital case subscript, that means total. And we capital, that's for DC. So similar on this side, you have VBE. So that's what I'm going to write. So you guys just pay attention to this. Sometimes I'm actually mix them up, but it's okay as long as you you actually understand what it means. Remember to distinguish this is a total current, total voltage, DC current, DC voltage, AC current, AC voltage. The total, of course, you know that is the DC plus AC. So total means just like superposition. You add a DC, you add AC to the DC on top. So it's like you have the total. So if you put these things together, it's like DC, and this is like AC, and then this is like total. So DC, actually, I drew it in a different wrong place, actually. Let me correct it. So this total means, and DC means DC, and AC means, so like this. So you add the DC, you add AC to the DC, you get the total, which is the AC plus DC. So those are some conditions you guys. Now, these two equations, guys, is something that we carried from previous lectures. Very important. These are the ones that we're going to use to derive our small signal model. So this process, you got to understand. And once you understand, it's fairly easy. Of course, you have to memorize the solution also as well. Of course, you can write down if you cannot memorize them. So those two equations, remember. So the equation, this one here, VGS minus VTN, that's the important parameter. And here, mainly just VBE is the important one because IS is given, it's the saturation current, and VT is the thermal voltage, 25 millivolts. If this is not given, assume it's 25 millivolts. Okay, so let's move on. So I'm going to do is we're not going to follow exactly what the book is doing to derive the gains. So we're going to just spend some time here to derive the small signal models or the equations at this point, and then we're going to move on to look at some examples that you guys have a better understanding what it really means. Okay, so for this, what we are doing here for this MOSFET, we are plotting this VDS as a function of VGS. So remember, this VDS is, well, actually we take output is VO. So by looking at this circuit, can you guys tell me what configuration is this one? Like common drain, common source, common gate. What do we call this? Huh?
Common source. Common source, yeah.
It's a common source because the source is grounded. We take the output at the drain, so the drain is not grounded. So if a common drain, the drain will be grounded. So it's a common source, okay? It's okay. Yeah. So now what we're going to do, you see this VGS, you see what this means? This is the total, okay? So lowercase v, capital V, capital GS, that's the total voltage, which means this has two components, AC plus DC. So what we're going to do is we start with the DC operation, and we're going to derive something, and then we're going to derive something that with AC unit. Okay, so let's go step one. VGS equal to DC only. So once DC only, we can write the current ID equal to now, of course, we are using N-type MOSFET as example. We can replace easily with a P-type MOSFET, so it's the same. It's the same thing. Yeah, you're right. So we're gonna use this capital D. Oh, so that's DC, right? So typically at this point, as we mentioned before, we said that VGS has to be larger than VTN, and VDS has to be larger than VOV, and VOV equal to VGS minus VTN. So those conditions has to met. That's number one step. And number two step, when VGS equal to VGS plus VGS. So the second step, we're saying that now, okay, so initially there was no AC, like AC is 0, right? So that's one, like really just in DC operation. So we're going to move on to say, okay, now I have AC introduced in that input voltage. Instead of DC only, now I have a little bit AC added on top of the DC. What's going to happen? Well, here we have to assume, now we have to assume still in saturation. Now, why do I say this is not the previous one? The previous one means the three conditions already met, so it is in saturation. But when you add an AC small signal onto it, if your small signal is too big, you know what's going to happen? You might take out of saturation, right? So that's why it's important to assume it's in saturation. Why? When we do this later on, we're going to tell you, okay, you get the small signal, you have to limit your small signal amplitude in a certain range. Otherwise, you're going to take this out of saturation, your circuit is going to give you output that has a cutoff at the top or bottom, right? So, okay, so we assume that. So now I'm going to do this. Let me see, what did I do? So, okay, so we're going to do this ID, which means the total. It's going to be 1/2 Kn. Because VGS now is VGS minus plus VGS. So we're going to simply plug in the DC and AC, replace that VGS with this DC plus AC. So we're going to extend this equation to So we're going to further extend this equation to this is very simple, just quadratic expansion of that equation. What's important at this point is that VGS is a small number. It's a small signal, so it's small. So you compare VGS square, it's becomes even smaller number to this term and this term. This can be like really small. For example, if this is say 1 millivolts, let's say this is 1 volt. So 1 volt times 1 millivolts, it gives 1. But this is 1 millivolts squared, it gives 0.0001, which means this is like 1,000 times smaller than the second term. It's even much smaller than the first term. So we're going to neglect it. So VGS is very small. VGS squared and can be neglected. Therefore, we have ID equal to 1/2 Kn VGS minus VTN squared plus, I'm going to multiply 1/2 Kn into the bracket. We get the two cancels, so we get Kn times VGS minus VTN. So this is the equation that we get. So now, as you guys see here, the first term equal to the DC current, right? Because that's the one that we derived. Look at the step 1. That's what we have. And so automatically, the second term is what? Is your small signal output, right? Because this is your DC, and this one is your output. So that we call that one is I. We use lowercase and lowercase, so that's going to be that. Therefore, we have ID equal to Kn VGS minus VTN times VGS. So that's your your small signal current that was induced by the small signal input of little VGS. So little VGS caused the output to have a component of little ID.
That's supposed to be big VGS inside.
Yeah, this is big VGS, right? Because this is the DC. So this is equivalent to the DC. So now we are going to go further from here. We get a term called GM equal to ID over yeah. So why we got GM? Well, GM is the one that actually we're going to use in the future very often. It's actually the transconductance. So what we are saying that if you give 1 millivolts, you're going to get a certain milliamps of output by multiplying this number. Now, for example, if VGS, let's say, is 2, VTN is 1, now you got this 1. If let's say if Kn is, say, 1 milli, now 1 millivolts are going to induce 1 milliamps. Right? So just this is a constant. So that's why we call it GM. So this is a GM constant. So by using this GM, we can easily say if VGS is 1, again, depending on what the GM value is, so you're going to like amplify this input to get your output.
Oh, so it's just like that anti-resistor amplification.
Yeah, it's like amplification. Yeah, it's it's called transconductance, but we're going to convert that into a gain as well, but in a moment. But at this point, you get it. You have voltage input. You induce an output current at that point. The ratio between that output current and the input voltage is called a transconductance. So apparently, a good amplifier would have a larger transconductance. So if I have 1 millivolts input, I want, say, 5 milliamps, which, it's going to be bigger, or 10 milliamps. So you don't want to say this is 1 milliamps and this goes to 1 microamps. That's not good because actually you're not doing the actual amplification. It becomes shrinking, right? So typically the GM value is around single digits to, and again, depending on the circuit design, it could be in a fraction, like 0 point something, to single digits to some tens, like 10, 20 something. But you rarely see GM more than 100. So typically it's in a 0 point something to like a 20, 30. So that's like a typical number. So next time when you do a problem, you find GM is 5,000, you know that you're doing it wrong because it doesn't happen that way. Okay, if your GM says it's 0.00 something, it's probably going to be also wrong. But of course, make sure GM has the right unit because typically the GM unit is, so GM
And it's a constant. GM's a constant.
is milliamp per volt. So that's kind of like milli in the units. Yeah.
Oh, yeah.
Yeah. So if you say it's 0.001 ampere per volt, you're not wrong because you're using the right unit, right? So it depends on what unit you're defining. Okay. So now we got this transconductance. What we're going to do is we're going to do this same circuit. I'm going to redraw the circuit here so you have better understanding when I write the equations. Okay, so we're going to restart. We're going to call step 1 here. So on each slide, we got to say a step 1. So here, what I want you to do is, since now we know ID and GM. Okay, that's of course we derived from previous step. I want you guys to write me together. How much is VO? Can we write with a kind of a loop equation?
That by R.
All right, so that's what you have, right? So now we are going to plug in. Remember, this ID is the total. So ID equal to, right? So you know what I do is I'm going to use this number, capital VO. I'm just sure bigger VO so you guys know it's the total. So it's going to be VDD minus RD ID plus ID. So it's going to be VDD. I'm going to extend this equation to okay, so I want to ask you guys, what when VGS, like the total voltage is DC only, the small signal is 0. What would you get for the what would you get for VO? I mean, it's the same thing, right? Yeah, so that's what you get. So we plug in this one into here. You get what? You get VO equal to VO plus minus. So the difference, I just simply said lowercase VO is going to be VO minus is going to be minus ID times RD. So this is your small signal output. So this is your DC output when AC 0, that's your output. And this is this is your DC output when the AC 0. So we have the total is equal to a DC voltage plus some change. So this change apparently is introduced by the small signal. So we can define this as your small signal output VO equal to the capital VO minus that DC VO, it gives you minus ID times RD. So what will you have? At this point, we can plug in, you go from the previous page. What we got ID equal to, then we can write down here. So ID equal to GM times VGS, right? So GM times VGS. So because we define the part as GM, right? So so this is defined as GM. So this is GM times VGS. Now we're going to plug in this one back into ID. So we get VO equal to minus ID so we're going to write down this minus GM. Okay, so now we got to output that little VO, which is our AC response to the input voltage, which is minus GM times RT times VGS, lowercase VGS, which is small signal. So if I take the ratio between output and input, what do you call? So we call it gain. So if we take so we call this a voltage gain. Also, it's very simple. It turned out. So my gain is going to be just minus GM times RD. So here you probably understand why you want a larger GM, because a larger GM will give you a large output. So we can have some numbers. For example, if RD equal to 10 kilo ohm, and the OGM is going to be, remember what our OGM is calculated is Kn times something. So let's Kn is 1 milliamp. 1 milli, that's the unit per voltage squared, right? And then we're going to have VGS equal to 2, VTN equal to 1. You see what we have now? We have GM equal to 1 milliamp per watt. So from here, we have our gain AV equal to minus 1 amp times 10 K, that gives you minus 10 volt per volt. So the unit is voltage gain, means your output voltage divided by input voltage. So volts by volts. So volt per volt. So what we are saying is that for this particular example, if we have R case 10, K is 1, VGS 2, VTN 1, where GM is 1, and our voltage gain is minus 10 volt per volt. So if your input is 1 millivolt, your output is going to be negative 10 millivolts, right? So millivolts, okay? It doesn't translate to volt. So if your input is 1 millivolt, your output is 10 millivolt, okay? If your input is 1 volt, output is 10 volt. Of course, if your power supply is not even 10, you cannot get to that point. That's why you have to limit your small signal amplitude. The other thing you guys remember, there's minus sign. So the gain is negative. So in AC world, what does it mean? Gain is negative.
going in the opposite direction of what we expect. Out of phase.
Not in opposite direction. That's not accurate.
And then the
It's AC, remember.
oh yeah, so
So it's not DC. If it's DC, you go this way and go this way, that's negative. But for AC, what does it mean? Yeah. Signal is inverted. The waveform is inverted. It's initially up this way, now it's going this way. Yeah. So it's 180 degree out of phase. Yeah.
assuming it's periodic. If it isn't periodic, it will just be inverted.
It's inverted, right? So, I mean, AC means it's periodical. AC typically means, sine wave, triangle wave, all that stuff. Yeah. Even if it's a noise, you can still decompose them into, using Fourier analysis to get fundamentals, third, fifth, two harmonics. Yeah. Then you analyze each one of them.
But like if you had if our changing thing was like a square wave, it would be from going from 1 to 0.
It's inverted also.
Inverted. So
yeah.
Also be shifted that it's not necessarily just 180 degrees.
But it's still 180 degree.
Yeah.
It is still 180 degree because you can't, it's up, now it's down. So, So what it means is that if you have, let's say your input like this, then now your output will be like this, right? So if if your input is square wave like this, your output will be like this.
Yeah.
So it's opposite, okay? So it's that simple, right? Now, from this point on, we can actually start to draw the small signal model. When we draw small signal model, we basically not looking at the physics anymore. We're looking at mathematics. So mathematically, and also the other thing to pay attention is that we are not interested in the DC anymore. We are interested just in AC. Okay, so the DC is only to form the biasing. And what we're doing in the process to derive it, once it's done, that's done. We don't care. As long as we maintain them in saturation, it's good enough for us. So we're looking about AC. So we're looking at AC, we're looking at mathematics. So when we look at mathematics, we're looking at a few equations I write down for you, and you guys construct a circuit from these equations. Well, first of all, we have this little ID equal to GM times VGS. And then we have this VO equal to minus GM RD. So there's just two equations. First of all, you have VGS coming in. You get a ID, which means this one is when VG change, ID change. So ID is the current, VGS voltage, and you have a GM in the middle. So what does this mean? This is a controlled current source. The current source ID is controlled by VGS. So you can easily think, okay, so let's get VGS coming in. And we have a current source. And this current source value is going to be GM times VGS, right? So controlled current source, the current is proportional to VGS. VGS here, that's here. Well, you might say, well, that has nothing to do with the MOSFET. Well, it does not, actually. It's just the characteristics of the performance of a MOSFET. Okay, so now we have GM, VGS. Now, the second equation says, well, we have to find VO, which is minus GM times RD and times VGS. Oh, no, you can rewrite this equation in a different way. You can write this equation to minus GM, which is, let me rewrite this. Minus GM. Oh, okay. Actually, why don't I just write it as like ID times RD? So what does it say? Is the output is simply RD times ID. So if I know ID, what would I do in order to get the voltage of ID times RD? You put them in series, right? So I'll put them in series. Now, of course, there's a little bit of, somebody might say, well, why can't you just put it here? You cannot do that. The reason is that current source has to have a path to flow. Okay? So if you put it here, it's okay, but then you have to close the loop. So you have to close the loop like this. So if you close the loop, yeah. So current flows, it gets a voltage of ID times RD. That's correct. Now, where would you get your output then? In this circuit. Can you get it here? Apparently, let's say we have a ground here, This is going to be ground here. So apparently, you have to get your output over here. So the current goes this way, right? This is your ground, and you get it. So you could do that, but for the future, for simplicity, also for, it's good looking. You look at it, you feel good about it, okay? So we don't do that. We actually do it this way. But what we're doing is, let me draw this for you. So this is GM. All right, so now we got the whole circuit, which means we put RD here, because now they form a loop. So current flows in this loop. Current flows in this loop. And OVO, we take OVO out here because current flows up from ground to this. So this is negative. Current can only flow from high voltage to low voltage. So this is ground, so this must be negative. And the total current is ID, so ID times RD gives you total voltage, so VO is ID times RD. So here, we got the equivalent circuit. Very simple, very simple. Now, of course, to get to this step, we had to go through the process of looking at the DC operation, look at how AC is added onto the input, and how the circuit quantities change, and how it resulted in some relationships. And then we use the relationships to draw our equivalent circuit. So this is what you get. Yeah. Now, of course, we're going to add something later, but at this point, you guys understand that this is what you have, the equivalent circuit of a MOSFET. Now, what's important about this? Because in the future, you are going to just use this equivalent circuit for now, plus we're going to add RO. Probably by next lecture, we're going to get to that point. So you're going to do that all the time. So sometimes we almost forget the BJT or MOSFET. We start, okay, let's replace with a small signal model. Now we're going to solve the circuits like I said in the beginning. So very simple. Now, before we jump into examples, let me do the BJT as well, so you guys have understanding. So eventually, these two circuits are so similar, even though the current and voltage equations are so different in the DC operation. But once you get to the small signal, they're so much similar. Not identical, but so much similar, okay? So let's do this. So for a BJT, so I'm going to do the same thing. I'm going to cut this into. So you guys remember the relationship between current and VBE. We have so this is the equation we have for a BJT. Yeah, so we're going to use the the generic equation now. So we're going to get to which symbol we're going to talk about. And it's going to be difficult for C's. But anyway, so what we're going to do is one. Okay. So what I'm saying here is that VB is the total is going to be two components. So in that case, what we're going to do is if VB is 0, we got IC equal to IS times e to the so that's DC. When VB, the lowercase VB is 0, you get this DC output. So now we're going to add. So we're going to have the two you guys see, right? So there's a DC VBE, there's lowercase VBE, and we add it. So now we're going to extend this equation. This is like a exponential, so e to the power. So we can decompose them into two terms. So this is going to be equal to IS e to the power VBE plus. And you guys probably know this. You can say this is VBE VT times e to the power so VBE is small. It's a small signal, so VB is small. So when B is small, we can basically say that e to the VBE VT equal to approximately, we can extend using like a, what is it called, Taylor series or something, 1 plus. This only true when VB is small. So e to the power. So now we're going to plug in this back into this equation. We're going to get oh, by the way, in that equation, in this equation, what do you guys see here? The first part half here. That's the DC current. So we're going to use that as IC. So now you have like this two terms. So I capital C equal to IC plus IC times so this has two terms. The first term is DC, or the second term must be AC, right? So of course you can also take the difference. You'll see that. So we're gonna little case IC now is gonna be IC over VT times VBE. So now we're gonna do the same thing. We're gonna do GM. GM is gonna be IC over VBE. So that's your GM. So this GM apparently has the same meaning, but the expression is different. MOSFET we get Kn times VOA. But here is IC divided by VT. But of course, you can still find out that because IC is milliamps, VT is millivolts, so it's like a millisieverts like that. Okay. So now we're going to continue to get the voltage gain. In order to get a voltage gain, I want you guys to look at how do you write VO? I'm going to write capital VO, capital O, equal to VCC minus I capital C times RC. It's just the same equation we had from the MOSFET, similar, just change everything C to D. So we plug in this equation to here. So we'll get VO equal to VCC minus IC plus oops. Right? So we just simply plug in that in here. We extend these two equations, the two terms. So now the first term is your DC voltage, one AC 0. So the second term is going to be your AC output. So that's your VO is IC times RC. And then we can plug in that IC over to here. We can get, because IC is going to be GM times VBE. So now it's going to be minus GM okay, guys, you got this equation here, minus GM times RC. And for MOSFET, we get minus GM times RD. So it's like very similar. The only difference is that this GM calculation is different. And the GM is with IC over VT. So in order to find the GM, you have to find IC and VT and this. So at this point, you guys can think about the equivalent circuit. Like when we derive the equivalent circuit, oops, what happened? What did I do? Okay, no, here, okay. Technology. So when we did, let's see. Yeah, I just want to go back to look at the equivalent circuit we had. So from here, we say, okay, there's ID, there's RD, so we had VO, and then ID is proportional VGS, right? So that's how we got equivalent circuit. So for the BJT, we can do the same thing. So first of all, we say, okay, there's VBE. And then we have here is GM times VBE. Okay, I'm gonna have this equation, I mean, this equivalent circuit right now, just like leave it like that. It's actually not correct yet. I'm gonna tell you why. But from those two equations, actually, it makes sense, right? You have VB coming in, and you have GM times VBE is the current in the collector, and you have output is minus IC, RC times IC. So everything here so far is correct. For that MOSFET, it's 100% correct because there's no current going into the gate. But for BJTs, you have VBE here, that's right. But look, over there, you have current going in, but here you have open circuit, right? So it's not correct. So to make it complete, what we need to do, we need to find what is this little like base current is, and then if we can find the current, so what we're saying is here. Let me see. Let me write down here. Step 9 is IB is not 0, right? Oops. So IB is not 0. How are you going to find IB? Well, remember what IC, when you find IC, your IB, well, in the DC case, equal to IC over beta. So ideally, we will go through the steps to derive the total current. Like we can derive IC, capital C. We can derive I, capital B, and then we find I, lowercase b. So not surprisingly, you will find that the IB equal to lowercase IC divided by beta. So we're gonna neglect the steps to do that. Yeah. But you will find out that the relation is still true for the AC. So which means if IB is IC over beta, if we plug that IC back into this equation, and you're going to find out that we're going to have something called R pi over here, and we're going to have IB at this equation here. So what that IB does is IB equal to, it's beta times IC, it's also equal to VBE over R pi. All right, so now we're going to move on to maybe next slide. IC over beta. Yeah, now you're absolutely right. Okay. So I'm going to redraw the equivalent circuit. So what we are saying is, so what we need to do at this point, we need to find what R beta is, because without R beta, it's going to be difficult to find the, in this particular circuit, to find the gain or to find the voltage gain and to find the GM, you don't need R beta. R beta is a resistance. It's a base to R pi. Yeah. No beta, pi.
Why is it called R pi?
No, R pi. Why called R pi? Because it's pi model. Where was my pen? Oh, here. It's called R pi. Okay. So we know that I beta, IB equal to IC over beta, right? And IC equal to GM times VBE, and GM equal to VT. We're going to plug that in back to see what we get. So, so IB is IC over beta. IB is IC over beta equal to VBE over R pi. And IC equal to GM times VBE. Okay, let me rewrite this. So IC. So IC is GM. GM times VBE over beta equal to VBE over R pi. So here we cancel VBE, you get R pi equal to beta over GM. So this is how we're going to derive the resistance. Of course, now we can plug in back GM to get because GM is beta, GM is IC over VT. So you can further to go to beta times VT or IC. So you guys see the only difference between the BJT equivalent circuit and the MOSFET circuit is the R pi. In MOSFET, there's no R pi because the gate has no current. No current is zero. So you have basically VGS floating. But in a BJT, the VBE is connected to R pi to form that current. So BJT is basically kind of a current amplifier. It amplifies the base current, IB. But MOSFET is a voltage amplifier, amplifies the VGE. So now we have the equivalent circuit. Let me see. Let me see what the next is going to be. Basically, maybe you know what? Let's go through an example. So you guys. Oh, okay. So I just want to stay on this slide for just a little bit. You know, if you draw VDS, in this case, VDS is VO. Your output is that VO. Because your AC is added on top of DC. So you want your DC kind of in the middle of the line. So what this line does is that this is a nonlinear relationship. What we're writing is VO equal to, my hand cannot touch the screen and I cannot write very well. So what we're writing is this. What we're writing this. So in this case, if ID is 0, you got VO equal to VDD. If ID equal to like a maximum, well, it's not 0, probably 0.2 volts. So what I wanted to show you guys the range. So if ID on the top equation, so your VO is VDD minus ID times RD, right? So if ID is 0, which means no current, so your output is actually your input voltage VDD. But if your transistor goes to trial mode, which means this MOSFET is going to have a very little voltage drop. So the bottom voltage is what? Is 0.2 volt. So your output range is between 0.2 to VDD. So that's how you can have your output swing between these two numbers. You cannot go below 0.2, you cannot go above VDD. So what we're saying, if we draw a circuit like this, let's say this is your VDD, which means your output is going to be so if your input is very big, then your output will be something like a cutoff at 0.2, and then it's going to be cut off at 10 volts or VDD, whatever. So between these two lines, the middle is the kind of the best, the sweet spot, right? So if you're in the middle, your upswing and the bottom swing is actually the maximum, right? So what we're saying is that if this middle point here is the best point to operate, so we call it quotient point. Now, if like we get just a few examples. If say your middle point is here. You see what happens is that you're going to have a cutoff at the top, right? So let's say if let's say your middle point is here. So what you're doing is you can have, I'm talking about really maximum output possible. So you look at this one, your operating point is too high. And this point, your operating point is too low. So the ideal point is in the middle. So when you are in the middle, you really get really, this is a good one. Yeah. So you get really maximum output. So that's why when in the future, when we do this like DC biasing, we want to make sure when there's no output, no AC, our bias point is best to be designed at the middle point between 0.2 and VDD.
Could you draw in that graph where all the different regions are? I'm just having trouble like interpreting it, like the triode region, saturation region, that in the VGS versus VDS graph.
I mean, on this way?
No, on the left with the blue.
Oh, with this one?
Yeah, all
Oh, where's the different regions?
like saturation.
Yeah, the middle, the part is the saturation, right? And then this is going to be the triode mode. And when you get to this point, that's in the cutoff. Cutoff means no current. When no current, your output is VDD. When it's in triode, you have 0.2 volts.
As VGS goes up, we go into triode. I thought when VGS went up, we went into
Yeah, when VGS go up, yeah, it will. VDS low, so it go to triode. But it's best to actually plot. I don't like this graph. I actually like this graph here. Is VDS as a function of VDD, or a function of ID. So for ID 0, you get 10. So it's the same thing, just saying that you want to operate in the middle point. So if ID 0, you get 10 volts, ID is maximum, you get 0.2 volts. So the other graph is probably more useful also. So let's quickly go through this example so we can conclude to the lecture. So what this example says, it gives you a bunch of numbers, like it's a MOSFET, VT is given, K is given, WL is given, blah, 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 and lambda is 0. Lambda 0 means no early effect, RO is 0. Now we're going to get to that next lecture. And here it says, okay, so for VGS 0, find VOV ID, blah, blah, blah. and what is the maximum symmetrical swing along the drain. And once you find the drain, translate into what is the input, what is the maximum input you can have, right? Okay, so well, first of all, let's solve for ID, right? So when the AC is 0, you find ID is K. And this is an easy one because all the numbers are given. Let me see what the numbers are. So VT is 0.4, Kn is 0.4, WOL was given at 10, times VGS is, how much is VGS? 0.6 minus 0.4 squared. So that gives you 0.08 milliamps. And this example in the book, so you guys don't probably have to write them. So this gives you 0.08 milliamps. And of course, in this step, we already found VOV is equal to VGS minus with 0.2 volts. And we also can find VDS is VDD minus RD times ID. And VDD is given at 1.8. Minus RD was 17.5 times 0.08. So that gives you 0.4 volt. That's number one. And then we want to find AV. We can simply apply the equation is minus GM times RD. Now we of course we need to find a GM. GM is Kn prime WOL. And Kn is 0.4 times 10 times 0.2. That gives you 8. GM is 8, 0.8. No, GM is not negative. AV is negative. So AV is minus, minus 0.8 times 17.5. 14 volt per volt, that's your voltage gain. Okay. Okay, so the next step, we're going to determine the range. To determine the range, like you guys go back to the circuit over here. So you see, when this thing is in child mode, how much do you get for VO? 0.2, right? So in child,
How did you know that? You just inferred it.
well, once in child, yeah, 0.2 is once in child, 0.2. That's what typically the number is given. Yeah, MOSFET. And BJT2, when in saturation, 0.2. Okay. Yeah. So when in saturation, 0.2. And we also find VDS is how much we found? (0.4), right? So you think about it. So here is 0.2. And here you have DC 0.4. So how much do you think your output range can be?
0.6, 0.2.
So your output range, basically, if you're more than 0.2 amplitude, this part is going to be cut off. right? So your maximum output cannot be more than 0.2 on one side. So which means 0.2, 0.2 should be a good number. So it's going to be 0.2 to the top range should be. So that's your range between 0.2 and 0.6. Huh? What do you mean open code? Oh, yeah, you can be blanket. Yeah, it's closed, I would say. All right, so that's your range. Now, given this range means your range is going to be .4 volt. So if your range is 0.4, how much your input can be? Well, our VGS is, remember, our VGS is, well, write down this way. Our VO is going to be minus GM times RD, right? So, and times VGS. So you simply just saying VGS is going to be VO minus divided by GM times RD. And then the minus sign, of course, just saying faces opposite, but the number is actually going to give you, actually each side is 0.2. So the amplitude is 0.2 times GM is 0.8 times RD is 17.5. So that gives you some number. I mean, I probably don't have to go to the actual number. It's 14.2 millivolts. Okay. So any questions? Yeah. Oh, no, the range doesn't matter. So the actual, when you calculate it, it's a negative, but when you actually translate into range, it's just saying from where to where. So 0.2 is a swing. Means from 0 to 0.2 or 0 to 0 minus 0.2. Yeah, it's a difference. Yeah. Okay. Yeah.
Why use 0.2 instead of 0.4 for VO?
Oh, it's one side. 0.4 is the range.
Not BDS is 0.4. That's right.
Yeah. VDS 0.4, but each side can be 0.2.
The minimum.
The distance from here to here and from here to here. So it's each side is 0.2. So it's your amplitude.
Is that the maximum value for VO?
Yeah, it's a maximum. Well, if you, well, I'm 0.2 will be one side.
Cut off.
Yeah, before you cut off, right? One side. If you take the whole range, it will be like 0.2 to 0.2, this will become 0.4. Okay, thank you guys. See you next time.
Confused because I thought you said that V out and VDS were the exact same.
Yeah, it is the same.